طيب، السلام عليكم ورحمة الله، حياكم الله. طيب السلام عليكم ورحمة الله. خليني أبدأ بس ببريف عن التوبيك sculpting noise and introduction to diffusion models. طبعا أنا اخترت يكون الشرح بالإنجليزي والمصطلحات بالإنجليزي لأن الهدف to build an intuition، وبعد كذا نقدر نقرأ من مصادر ثانية مختلفة، الأوراق وهذا إلى آخره، ويكون عندنا الترمينولوجي والمصطلحات اللي نحتاج نعرفها عشان يكون عندنا خلفية كافية. طيب راح أتكلم عن 5 أشياء تقريبا. راح نعطي introduction للgenerative models. نبي يكون عندنا common ground، يكون عندنا فهم للgenerative models، ونتأكد إن كلنا عندنا خلفية عن الgenerative models بشكل عام. بعد كذا traditional generative models، صراحة I wouldn't say traditional، بس يعني for the lack of a better word I will call it traditional generative models. بعد كذا we will talk about diffusion models, and then we will talk about score matching, which is another way to implement it. And then we will discuss briefly why we made the move from GANs to diffusion and what actually cases that require us to move from GANs to diffusion. And then we will have a discussion if any questions are present from the audience. قبل ما نبدأ this is a two-way discussion، فأحتاج الكل يتفاعل ويسأل at any time. interrupt me، قاطعوني، أسئلة whatever at any time، عشان بس تكون الفائدة أكبر. طيب خلينا نبدأ ب definitional generative models. So a generative model learns to generate new data samples that resemble the training data. So if the training data was actually a set of cat images, we would actually expect the generative model to generate cat images, and it won't generate something outside our data distribution. So the way it does that is by capturing the underlying distribution of the data. So basically, it tries to model how the data is distributed from the set of all possible data. So if we have cat images, it will learn how the cat images are distributed apart from, for example, any other image of a car or of an airplane. And by modeling the underlying or capturing the underlying distribution, we hope that we can create new instances that look similar but not identical. So we would look at images of cats with new colors that we didn't see in the training data, but somehow it would look similar to the cats in the training data. We mentioned the word distributions, so let us just discuss a little bit what is a distribution. So in our case, a data distribution is just a probabilistic distribution that describes how the data points are spread in the feature space. So the feature space in this case would be the pixels of this specific image or any other image, and the PDF or the probability density function is just a function that maps the image into a probability space. So if our generative model or our data set is mostly comprised of cat images, we'd expect the PDF to map higher probability values to images from the data set. So at peaks, you'll find images of cats if the case was a data set of cats. Whereas, for example, if we had an image of a human, the PDF would map it to one of the values, which is like the lower values, close to 0. Of course, the peaks here represent data points, or like the distribution of the data points where we have more dense representations. So in this case, each peak could be defining a different breed of cat, but they're all cats. But we could have, for example, like a Bengal cat or any other type of cat. So this is briefly what a data distribution is. Okay, so let us begin by GANs. GANs have been actually quite the hot tech for the past period. If I recall correctly, it was one of the models that actually created high fidelity or high quality images. But briefly, GANs are composed mainly of 2 neural networks. The first network is called the generator, which is tasked with creating the data or generating the data. And then we have a discriminator network, and its whole purpose is just to evaluate the data. So the discriminator is just a classifier. It's a binary classifier. It predicts either the image is real or fake. Real being it's an image from the real data set that we are trying to train on. So for the same example, it will be an image of a cat. And if it's fake, then it's generated image. And the generator tries to fool the discriminator by generating images that actually look similar or look similar to the real samples from the training data. And the discriminator has to distinguish between those two. So the way it works is that we pit the two networks against each other. So the generator tries to generate, I would say, realistic samples, and the discriminator tries to tell if it's actually coming from the generator or it's from the real data. So it's 1, for example, is real, 0 is fake, and then both of them are penalized based on the performance of the other. So we are hoping to pit them, and both of them will try to improve each other. As the discriminator gets good, we hope the generator actually improves and generates more images that are able actually to fool the discriminator. So this is in a nutshell how GANs work. We will discuss some of the limitations of GANs later on once we define the whole generative models we're going to talk about. So moving to variational autoencoders. So let us just look at the name at the beginning. So we see the word variational. So variational means that probability is involved. And then we have autoencoders. And let's break autoencoders as well into two words, auto and encoders. So auto here means self, and an encoder is just a model or a framework that transfers data from one form to another form. So as the name indicates, autoencoder would convert our input data into some representation, and then it will convert it back to the first original representation, hopefully the same. So variational autoencoders, it combines the autoencoder with probabilistic modeling. So we know probability now is involved. Distributions are involved in this case. And the encoder of a variational autoencoder actually maps the input data into a latent space representation. So a latent space is just the feature space inside the model itself. And then the decoder reconstructs the original data from this latent representation. But please pay attention here. What the variational autoencoder or the encoder itself in this model outputs is means and variances of a probability distribution within the latent space rather than a single point. So basically for a normal autoencoder, you'd be having, would be having just the variable z, which is a vector inside the latent space. But in the case of variational autoencoders, we'll be having actually parameters that are associated with a Gaussian distribution. And then we sample from these parameters. And then we predict the output by reconstructing it. But bear in mind, for us to train this, for us to be able to do backpropagation, we need the sampling process to be differentiable. We need it to be in a differentiable form. Lucky for us, if we want to sample from a Gaussian distribution, we can do so through this equation by actually just taking the mean and adding the variance obtained from the model itself. So we get the mean. So I'm sorry, I forgot to mention this. For each latent variable, we have a separate mean. So we have 3 means here and 3 variances. And so we just add the variances with element-wise product with an epsilon. Epsilon here is just a random noise we pick, and we sample it from a standard Gaussian distribution. The whole purpose of this multiplying and adding the noise is basically because this whole network is deterministic. Over some time, all the weights would converge. And if we have no stochastic term, we will always keep generating the same inputs and same outputs again with no variation. So sigma or epsilon, in this case, would actually help us to change or generate samples that are similar to our inputs. And that's like another cool feature of variational autoencoders, is that the latent space is continuous. So if we portray the model over images of cats, we can slightly tweak the noise, and we can actually obtain a cat that is similar, depending on how far or how large the epsilon we do add to the model itself. Basically, we have a well-structured latent space where more likely images or more similar images reside next to each other within that space. Okay, so that's so far for generative models or traditional generative models. Let's dig into diffusion. So I want first to start by describing the concept. So just follow with me on this first bullet point. So a diffusion model is just another type of generative model. We expect it to produce new data. For example, images, could be audio, could be videos, could be any sort of data we have, because it's data agnostic, doesn't care about, modality agnostic, doesn't care about the modality. It does so by simulating a forward and reverse process analogous to the diffusion physical process. So if you look at the image here, we have a beaker that contains water molecules, and then we add few drops of dye. And if you ever try this experiment by yourself, you will find that over a certain period of time, the dye actually spreads evenly and it reaches a state of equilibrium. So we say that the dye molecules actually diffused throughout the whole fluid or liquid, in this case water, evenly. And this is the diffusion process. In our case, the water molecules represent our training data, and the dye represent the noise that we will inject into the data itself. And then over time, we will inject more noise until we have completely noised images. So this is like the inspiration for the diffusion process. So diffusion models gradually add noise to the data and learns to reverse this process. So it does those two in parallel. So we add noise and we also learn how to reverse this process of adding the noise. So let's break it down into two processes. The first one we'll call the forward process or the diffusion process, where we start adding gradual noise in small increments and diffuse it throughout the data until we have a completely random sample. Or in this case, let's just take images as an example. We have a completely random image. And the reverse process is basically us trying to reverse the added noise incrementally and also gradually. Let's take a look at this example. So in this video, you can see the colors are being mixed, and I think it's a very nice analogy. So if you look at this, if we know exactly how many turns we did in this case, so I think it's probably roughly 6 turns, if we try to reverse this process, knowing in our case how much noise we added, we can somehow go back to something very close to the original data set. And I think it's a very nice analogy. Okay, let's take a look at one way to implement denoising diffusion probabilistic models. This is one way to implement diffusion models. It's actually one of the ways that popularized these because it's a very simple method. So let's take a look here. DDPMs actually assume that our process follows a Markov chain. So just for the sake of explanation, a Markov chain is just a chain where each state only depends on the previous state. Yani X at time t depends on the previous one. It doesn't depend on the future ones. So we only depend on the previous states that we were on. At time step 0, x0, we have an original image which should be completely free of noise. And at time capital T, which is the time we decide it's a hyperparameter, it could be 2100, doesn't matter, we would have a completely noised image. And this is a random Gaussian image. Okay, so basically, how DDPMs actually remove the noise, it's through a very simple method. It learns a denoising function. By function here, we mean a neural network that maps a noisy version of the data to a less noisy version. As we mentioned, less noisy because we do small incremental changes to the image itself. We have here two probability distributions, Q, which is just a Gaussian distribution generated by adding a Gaussian noise, because normal distributions are closed. So whenever we do any linear transformation on them, the outcome is still Gaussian. And so as long as we keep adding small incremental changes from a noise that is sampled from a standard Gaussian distribution, distribution will stay the same. And for the reverse process, the denoising process, we can see that our distribution is being parameterized by theta, meaning that this distribution is being estimated through the weights of a neural network, theta here representing the weights of the neural network. And it's also modeled as a Gaussian distribution, where the mean and variance are predicted by the neural network. And this is where, this is why actually we chose it to be Gaussian, because we have closed form solutions for these, and it's actually much more easier for us to deal with those. So let's take a look in details how the training process actually works. So just look at the algorithm here on the right side. So we'll just, by repeating until conversions, and then we sample from our distribution. So basically here we're taking one sample from our training data set, one image, x0. We sample a random time step from 1 to capital T. Why do we sample time? Because we need to input time as an input to the model itself. We need the model to learn the notion of time. We need the model to know at which step it is now. It's either at xt or xt minus 1, or in this case x0, which is the first time step. And then we sample epsilon, which is a noise that we sample from a standard Gaussian distribution, zero mean, and we have identity covariance matrix here. So variance basically is 1. And then if you look at this process, just ignore everything else. Epsilon theta is the output of the neural network. It's a function that takes a mean, which is square root of alpha bar t, x0, plus square root 1 minus alpha bar t, epsilon t. If you look, this looks similar actually to the previous equation here, where we sample from normal distribution. We have mean plus variance multiplied by a Gaussian random variable. And if you take a look, it's actually similar. So now we have this to be the mean, this to be the variance. And we can still tell that it's actually taking an input as a Gaussian distribution. Let me brief you about what is alpha in this case. So whenever we want to do the noising schedule, we mentioned that, the noising step, we mentioned that we want it to be incremental in small incrementations. Why we want to do that? If we add too much noise at one step, the model will fail to denoise that. It will be much more difficult. And in the same manner, if our added noise is too small, the model will fail actually to learn something useful. So just for the sake of simplicity, we will assume that we have 1,000 time steps, and we have a linear noise schedule starting from beta at time 1 to be 10 to the minus 4, and beta at time t will be 0.02. So we have 1,000 steps. It's a linear schedule. We can just map the increments directly. What's the benefit from this? We know for a fact that beta 1 will be corresponding to this image, and beta at time t, which in this case would be 1,000, would be after completely noising the image. In this case, if we want to compute the noised image at time xt using only these two parameters, it means that we have to compute all the previous time steps. So if we assume that t is equal to 500, it means we have to do 500 computations over the images just to arrive at one value that we want to use at this time. And this is actually inefficient. So the authors of the paper came up with a reparameterization trick where they substitute alpha t to be 1 minus beta t, which is just the value of the noise. Just take it as the value of the noise now. And so this allows us actually to compute the noise at any time step directly by just taking the cumulative product of the noise levels, and we can directly then multiply it with the original image, which is this one, and then we can add the sample noise, which is this one. So on demand, we can compute the noised version of the original image at any time step with no with less cost actually compared to just generating the image each time. Okay. Once we added the Gaussian noise to the image, we have now the noised image. We ask the neural network to predict the noise, which will be in this case epsilon theta. And then we just use the mean squared error to compare with the epsilon that we added. So basically, in a nutshell, let's summarize what we are saying here. We add some random noise to the image. we know the value of that noise. We ask the neural network to predict the value of that noise, and then we just compute the difference and we minimize that, given the fact that we also factor time, because time here is really important. And we repeat this step until these steps until convergence. We take another sample, we sample a random time step because we need to go through all capital T's. So we need the model to learn the notion of time now. And we sample a random Gaussian noise. We add it to the original image, and we already added it, so we know how much it is. So we just subtract it from the output of the neural network itself. And this is, in a nutshell, how DDPMs actually work. It's a very simple method, and the implementation is actually way more simpler than how the algorithm looks here. Okay, now we learned how we train it. I think it's time we take questions. So if anybody has any questions, I'll be looking at the chat for 1 minute or 2 minutes. Okay, so we have a question from Omar. So basically the GANs are responsible for continuous learning. I'm not sure if I understand this part of the question and why they were a hot topic, if I may ask, because they were one of the models that actually generated high fidelity images. And the quality was actually really good compared to previous methods, especially since we're implementing it through deep learning, so we can access our large volume of data to train such models. Okay, let us continue. So we learned how we train the DDPM through the forward noising process. But once we train the neural network, how do we generate images from this trained model? It's actually the same process. Since we start from the last time step, we always want to generate from completely noise. We don't have the image. So we will start by sampling a completely noisy image from a standard Gaussian distribution. And then we will loop over time step t because we start at the reverse. So we will start from capital T. In our case, for example, t is equal to 1000. And we will loop until time step 1. We will do the following. We will sample a random noise if time t or time step is greater than 1, and else this will be 0. We'll get back to why we need this. But let's just focus on this part. We ask the neural network to take the noisy input image, which is this one, and the time step t, which is this one, capital T, which in our case will start from 1000. And then we subtract that noise, a scaled version of that noise, from the original or the originally noised image or the complete noise. And in our case, because time step is greater than 1, we will add some random noise. The whole purpose of this noise is just to introduce more stochasticity onto the model. We want to steer the generation process into exploring more of the space itself. So this will allow us to actually have more diverse outputs. Of course, we will not do that at time step 1, because if this is equal to 1, we need the original image with no noise, so we don't want to add this part. But we will keep repeating x at time t minus 1. We will input the same previous one, x at time t. We will predict the noise, subtract a scaled version of it from this noisy image, and keep repeating until we reach time 1 or until we are satisfied. But please bear with me on this part. We don't have to start from time step 1000. You could start from 50, you could start from 100. because what we are doing here is that we are doing a trade-off between quality and speed. Because if I do 1,000 iterations, it means I do 1,000 predictions through the neural network. Maybe I don't have the capacity or the time to handle that. So maybe I only want to do 50. So I'll start with t equal to 50, and I only do 50 denoising steps. Probably I'll get an output similar to this, but it's a test time compute kind of trade-off, where whenever we want to have faster outputs, we reduce the time steps for the denoising, or we can go for full, and the more we put as time steps, the more or the higher quality until a certain degree we get from the output. And this is how we basically generate or sample from DDPMs. Another way to do diffusion is through something called score matching or score-based diffusion models. So score matching involves actually layering a score function, and we will discuss briefly what is a score function. It's just the gradient of the log probability density, which is this one. We have the gradient, and this is the log probability of the density. So this density function actually represents the data distribution of our images. So if you recall, when we mentioned distributions, we said that we have a density function that maps images to space where actually our data set is comprised of cats. So we have peaks on images of cats and high values actually on images of cats, and we have peaks there on the 3D representation. And in this case, it would be similar, but in this case, we will take the log of that probability density function, and then we'll take the gradient. So look at this image here. If we try to plot the density function, it will be it will look like this image. So in this case, we have higher density. So in our space, the images of cats actually reside more here, a little bit here. And the score function, since it's the gradient, it means that it will represent something called the vector space. Since the gradient involves actually vectors in this case, this score function will always point to the direction of the highest density. If you look at these arrows, they will always point to the higher density in the space. So somehow we can tell that the score function is an indicator or a way for us actually to go to the higher density. And I think a very nice analogy for this part is if you look when we try to optimize neural networks, where we compute the gradient, and the gradient tells us the direction of greatest change. And in this case, the gradient would tell us that there is a nearby minima, and it will guide us through the minima. The score function would do something similar in this case, and it will try to guide us to the real distribution. So for example, if we have a distribution of noised images, and we have the real distribution of the real data, the score function will try to move us or tell us how to go from a noise distribution to a real image distribution. So we go from this one to this one. It will guide us through the way or the path we take to go through here. So I think this is in summary how I would simplify score functions. So I think I will also take questions now. So please feel free to ask. Okay, so no questions, let's continue. So I think one other interesting way to look at this, in contrast to the DDPMs, is that score matching actually can be continuous in times instead of strictly being a Markov chain where we have discrete time. We can implement it continuously. So I wouldn't get into the details of this, but this is a stochastic differential equations. This is a stochastic differential equation which basically states that the difference in x, so you can take a look at xt minus 1, which is this term, is equal to the added noise or the variance in this case, multiplied by as we mentioned, how we sample from a Gaussian distribution. This is Brownian motion, which will correspond to a Gaussian distribution in our case. But let's not dig into this. It's not important. What we are trying to do here is to build an intuition. Okay, so if we assume the noise to be Gaussian, so basically the noised image is equal to the original image plus some epsilon noise, and this epsilon noise is from a standard Gaussian distribution. Our ugly score function, the one we showed earlier, which is the gradient of the log prop of the PDF of the dataset, would only simplify to be the difference between the two images, in this case the noised image minus the original image divided by the variance in this case. Okay. Eventually, since we have the score function here, I'm sorry, what we are trying to optimize is that for our neural network to estimate the real score function. We mentioned earlier that if we assume our noise comes from a Gaussian distribution, we can simplify our score function to be the difference between the noised image and the original image divided by sigma square. And of course, summation for n is over the number of batches, and we normalize by the number of batches. And this is also a mean squared error optimization. The interesting way to sample from the score function, so we mentioned here, we generate through this process, which is predicting the noise and subtracting the noise from the image at each time step. The way we do it for the score-based model is through something called Langevin dynamics, which is a way to sample from stochastic differential equations. In this case, if you bear with me, this looks really familiar. This looks like the update equation for the gradient descent. So if you assume this is the current parameters or weights of our neural network, alpha I would be the time step, no, sorry, the scale or the learning rate. This would be our gradient descent, because if you recall, it's just the gradient of the log props. So this will be our gradient, and then we could consider this just as a regularization term. So if you look here, eta k or eta t is sampled from a Gaussian distribution, which is also a noise, and alpha I. So as we always mentioned, we add this term just to introduce some diversity in our output, because the whole model is still deterministic. And alpha I is just a small step. In a nutshell, I think this compares or showcases the differences between score-based diffusion models and DDPMs, and we will take any questions about them once we end. I think let's answer the question of why we need to move, or why we want to move from GANs to diffusion. If you ever try to train GANs, they are notoriously unstable. It's very difficult to stabilize because you have two neural networks and you have to balance the loss between them. And most likely it will be a nightmare to stabilize the training process. Diffusion, on the other hand, trains an MSE loss. I wouldn't say diffusion is straightforward stable, but it's much more easier to train than GANs. And maybe let me highlight this. Diffusion by itself is not an architecture, it's just an objective. So you could implement diffusion over transformers, or you could go through what was previously the more common method over unit architecture. But it's actually much more easier to stabilize compared to GANs. And also the diversity of the output. GANs are actually prone to mode collapse. Mode collapse, if you look at this image, if you consider these peaks as modes, what would happen sometimes in GANs is that they would collapse and they would generate the same output, or generate just specific type from our distribution, failing to diversify the output. And this is also one other limitations of GANs. As for diffusion, it has more modeling capacity, so it can output more diverse outputs. The comparison, I would say GANs outputs could be less sharp compared to diffusion outputs. especially, for example, if you try to train audio models, I think you would have much more higher quality output using diffusion than if you try to do with GANs. As for the convergence, of course, as we mentioned, we need to balance the two networks, because if one of them actually outperforms the other, your training collapse. For diffusion, since we break down the problem into small stepwise increments, we are actually having more stable I wouldn't say faster convergence, but actually better. Okay, the computational cost. GANs actually generate the whole image in one single inference step. So it directly generates the output image instead of going through steps. As I mentioned earlier, in diffusion, actually, you can have a small trade-off by decreasing the number of steps, but that will be dropping the quality of the output. So if you'd rather have a faster inference, it would translate into lower quality compared to if you go through the whole steps, given some specific upper bound, because at sometimes it will saturate beyond certain number of steps. Okay, thank you guys so much. I think we can now take all the questions you guys have.